Look around you. The smartphone case in your hand, the dashboard of your car, the casing of medical devices in hospitals. These objects share a specific kind of geometric perfection. Millions exist, and every single one is an exact, flawless clone of its original design. For most of human history, metal or plastic with extreme precision. But cutting takes time. When you produce 2 billion smartphone cases for a global market, carving them out one by one is far too slow and incredibly expensive. The solution to this volume problem is a formative manufacturing technology called injection molding. Instead of cutting material away, this process forces liquid material into a hollow cavity, letting it cool and harden into the exact shape you need. It acts as a high-speed bridge between digital engineering and physical reality. A complex design that took months to model on a computer can be physically duplicated, down to the millimeter, every few seconds. The process starts with the raw material. Most injection molded parts begin as tiny plastic granules. These are thermoplastics, materials like polycarbonate for tough phone cases or polypropylene for flexible hinges, often mixed with colored pigments to get the exact hue required. This diagram shows the core machinery of the process. Raw pellets are poured into the machine's hopper, a conical funnel at the top. Gravity pulls them down into the barrel. Here, they encounter the reciprocating screw, a long, rotating shaft surrounded by heater bands. As the screw turns, it pushes the plastic forward. The intense mechanical friction, combined with thermal energy from the heaters, completely melts the solid pellets. What started as hard plastic gravel is transformed into a thick, highly viscous liquid. Once enough molten plastic gathers at the front of the barrel, the screw stops rotating. It suddenly acts as a massive hydraulic ram, plunging forward and injecting the liquid plastic into the mold with immense force. This first half of the machine exists to build up intense thermal energy and kinetic pressure. It primes the material for the physical transformation that happens next. The molten plastic blasts out of the nozzle and into the heart of the system, the mold itself. To keep the liquid from bursting out, the machine uses a clamping unit. The pressurized plastic pushes outward with incredible force, so the clamp pushes inward, applying hundreds of tons of pressure to keep the two halves of the steel mold perfectly sealed. This shows how the liquid is forced into every microscopic corner of the cavity. It takes on the exact external shape of the design, easily forming the sleek curves and parallel ventilation slits of an automotive grille. This diagram shows the specific mathematical rules engineers use for the internal structure. By controlling wall thickness and adding support